want to talk to you about today is to give you some small insight how using an approach, we can call it an E-approach because we're using a lot of computers in it, can really help to develop the future of cement and concrete. First of all, I just put in a quick slide of where I work in Lausanne. And I hear this is quite appropriate because I think later on you will have a presentation about this rather interesting building here, which is our new so-called learning center, the Rolex Learning Center. The message I want to leave you with today is that because we have this pressure now to develop more sustainable concrete, the inevitable consequence of that is concrete is going to be more complex. And to help deal with this complexity, we really need to have models that are based on the underlying scientific mechanisms to help us be able to better use concrete in a sustainable world. Now, we have to remember, and people often forget, that concrete is actually an intrinsically very low energy and very good material from an environmental point of view. It has lower energy and CO2 content than almost any alternative materials. And it's partly because of this that concrete is by far and away the most used material in the world. And because of these enormous quantities, this means it accounts for more than 5 to 8% of man-made CO2 production. So this puts a pressure on us to really reduce this, to reduce the environmental impact still further. And this is particularly important as the demand is forecast to rise substantially over the next decade. So not only have we got to improve the concrete we have, we've got to produce more of it. And this is a big challenge, a challenge presented by the growing world population and the fact that people want and aspire to better standards of living. Now, contrary to what is often written in the press, there's really no magic bullet solution of this. We often see every few months somebody has developed this wonder concrete that can eat CO2, and while these solutions may be part of the problem, not least because of the materials available in the Earth's crust, we're really limited in possibilities. And really we're quite limited to the elements that are presently we find in cement and concrete. It's quite interesting to see that these 8 elements, oxygen, silicon, aluminium, iron, calcium, the alkalis, and magnesium, account for 92.8% of the Earth's crust. So we're not going to find any solution for building houses in these rest of the material here. But of course what we want to do is to reduce the calcium content, because it's that calcium content that indirectly leads to the emissions of CO2. And in doing that, unfortunately what we're going to do is we're going to change the chemistry and we're going to change the way that concrete reacts and performs. So just to give some examples, what we've been doing so far is reducing the so-called clinker factor by substituting cement by these things like fly ash and slag and things like that. Unfortunately, we see that these materials that we use to substitute cement are not available in all that large quantities. So it's no good saying we've just got to use more of them. There aren't more of them to use. And in the future, we're going to have to imagine a more diverse range of materials to substitute for clinker in cement. And all these things are going to mean that the concrete becomes more and more complex. Oh, sorry, wrong one. Okay, so how can we meet this forecast for growing demand? I think we can do this if we can better optimize our solutions according to the local raw materials available and to the applications. And I think this has to be done in a wide variety of ways, some of which are shown here. And collectively, I call this approach an open concrete approach. If we can have concrete which is open to be able to use an increasingly wide range of materials, I think this is the best way we can confront the need for more sustainable materials. But if we're going to do that, then we have to know how the concrete is going to perform. What really we want to be able to do is to go from the composition, the mixing, the time, the temperature, etc., to the performance expressed by a diversity of things, for example, the early properties, the properties during hardening, the durability. And I think we can ultimately do this scientifically if we can well understand the microstructure, which is centrally positioned. The microstructure is formed by all these parameters here, and then it's that microstructure that governs the performance. And we really can start to understand how that microstructure is formed by using fundamental scientific principles like thermodynamics and kinetics, which is what I'm going to talk a bit more about today. So here's an example of a final microstructure of concrete seen at the microscopic scale. You see this is 10 microns here, and what we can see the grains of cement which have partially reacted to give us these reaction products, and still between these reaction products we have the dark porosity, and it's usually that porosity which is controlling the properties such as the strength, such as the durability, etc. Now you can see this is rather complicated, so what we want to be able to do is to generate this microstructure in the computer. And here you can see the results of a simulation. It's a simulation in 3 dimensions, and basically the idea is that these red grains that are the grains of cement, they are hydrating, and you see they're producing products that fills in the spaces between the grains. So this is how we want to approach this question of linking the composition to performance. But I think, first of all, we have to really ask ourselves a bit more the question, does it really matter what the microstructure is? And if we believe what you find in a wide variety of textbooks, if you believe this result from Powers in the 50s, then microstructure is completely irrelevant, because this graph here says that all this matters is the total amount of porosity and not how it's arranged. But if we look at other results, okay, we can see nice correlations, but the correlations change with the material. We can see apparently bizarre things, such as the fact that if we introduce silica fume, the total porosity increases, which is in total contradiction of the fact that we know these materials can have much higher strength. And more generally, if we look at a whole group of results, what we see is the picture is much more complex. And, here, for example, what this says is if we have 20% porosity, we might have a strength of 5 megapascals, or we might have a strength of 60 megapascals. And so that approach is totally useless for building a building, because we have to know the strength with a bit more precision than that. Here are just some simple diagrams that show you why the arrangement of porosity is important. Here we have the same total porosity, but with different arrangement we get very different stress distributions. And here's a very extreme example of a material with a very low porosity, but very, very easy to break apart. So we would see similar kind of observations for other properties such as durability. So we think it is really critical to follow this approach of really building up the microstructure by thermodynamics and kinetics to be able to give us our final performance. And this is where our work has focused over the past few years. So in this context, we've developed a model. Our model is called MIC. This is the little logo for MIC. MIC stands for microstructure. And this is a completely flexible model in which you can put in your fundamental mechanisms and use them to generate a microstructure. The reason we invested in this new model is because really we wanted to be predictive. We didn't want to hardwire anything in. And what you find is that other microstructural models, either they have a resolution limit, often around 1 micron, and 1 micron is really quite large when you're talking about the pores that you find in cement, paste, and concrete. And other models, they don't really take in the mechanisms, they just really encode the empirical information against experimental database. So it was quite a challenge, really, to develop this model because it had to be quite fast. And you see that when we started out, we had a simple model which could model 10,000 particles in 2 days. Quite honestly, that's pretty useless for doing anything practical. And now, with the advances in computation, we have it down so that we can even model systems of around 2 million particles in 10 minutes, which is really starting to be realistic for what we want to do. Just to give you an example, this is a particle size distribution of a typical cement, and you see to capture the range of particles, you've got well over 2 million particles in a size of about 100 microns. So the advantages of our model is that the way we do it, it means there's no lower resolution. We can have total flexibility as to how we generate the products, and we can do this according to what we see experimentally. The whole kinetics is integrated in the model, and we can have complete tracking of the solid and liquid phases. So these just shows you some kind of weird and wonderful ideas of the kind of things you can model. That's all very well, that's pretty pictures,